Morning. Today we're going to continue with our discussion of gauge theory. Last lecture we looked at abelian gauge theory. So just to remind you, a gauge theory is something that's invariant under a local symmetry group. So far in our discussion of quantum field theory, before gauge theory, we've looked at global symmetry groups. For example, the Poincare group or discrete symmetries. We haven't covered them so much, but these global symmetries act on the whole theory, taking one configuration defined over all of space-time to another. A local symmetry group is one that acts independently of space-time location. So we have some local quantity, like a Dirac spinor. This is all classical, this discussion so far. And we allow ourselves this spinor to undergo a local phase transformation, which is independent, and I'll put scare quotes here, we allow this transformation to take place with an arbitrary phase factor at every different location in space-time. Now, as we discovered, actually, I imported an assumption when we just started discussing theories invariant under these symmetries. We actually turned out we assumed that these were differentiable. So we started by demanding that our theory is invariant under a local phase change at every location independently, an independent local phase change for every location in space-time. And we ended up assuming, as we built a theory invariant under this transformation, that these are at least one-time differentiable, these phase factors here. And of course, the other thing we discovered is that if you have more symmetry, then there are less things that are symmetric under that bigger symmetry group. So our new symmetry group is a combination of Poincare plus local gauge. Well, every time you want a symmetry in a theory, that imposes a constraint. You can't have, it's not really possible for a theory that's symmetric under more things to be less constrained than a theory that's symmetric under fewer things. So when you want that a theory is invariant under a bigger symmetry group, you just have no chance. When you want that it's invariant under a bigger symmetry group, there are fewer things that can be invariant. And in fact, what we found is that there are essentially only strictly local terms that are invariant under this local gauge group. It's a bit of a bummer. So you can't find interesting Lagrangians with dynamics without, which have manifestly Poincare local gauge symmetry. Can't do that unless you introduce an auxiliary field, a helper field, which tells you how to define derivatives. So that's where we got to the covariant derivative. Except I used a plus. I think. No, I had a minus after all. A plus. All right. So by introducing this helper field, this helper field allows us to compare things at different locations in space-time. It's like setting an agreed upon reference frame at every location in space-time. We could build a derivative-like object. It's not the derivative anymore. I mean, because we've introduced more degrees of freedom. So this is not a derivative. It's in the standard sense of a derivative. It's not defined as the limit of the difference of two things directly. We had this parallel transporter object coming in here. And so once you have this helper field, this gauge field, well, then it's easy to write down terms which are invariant under gauge transformations that are non-trivial. In the sense that they give dynamics to the Dirac field. So this is, as I stressed in the previous lecture, when you have more constraints, there are many ways to deal with having more constraints. And one of them is to introduce more degrees of freedom to accommodate those constraints. So it's like you go from an undetermined, overdetermined set of equations to an underdetermined set of equations. That's exactly what we've done here. We've just insisted that our theory is invariant under Poincare and local gauge. It's up to us how we interpret invariant here, and by invariant we mean representation of. So you can choose a different representation where you have additional degrees of freedom. Here they are. These extra fields here are also transform according to this local gauge group here. So that's a different representation. That's one way of looking at what we did in the previous lecture. We chose a different representation of this local gauge group. In the first representation, where we just took the local gauge plus Poincare to act on the Dirac field, then we were stuck with these terms. There's no avoiding it. But then we say, okay, well, what do we mean invariant? We mean representation of. So why don't we take a different representation, one which has additional fields in it, and then build theories that are invariant under this new representation, including this additional field. And that works. We get non-trivial dynamics like that. We get terms like this which are invariant. Because there's no mu here. That's the story for this transformation here. And so at the end of the last lecture, we wrote down the Lagrangian. Oops, no traces just yet. For this new representation of these symmetry groups. And this F here is this curvature tensor. That's a way to give this helper field dynamics as well. I mean, it's all very well to have this field A mu as a classical object that sets, set once and for all, but then that gives you a large number of experiments you have to do before you can turn that theory to be predictive, because you would need to know what is this field everywhere in space-time. A far more, in keeping with the role of fundamental interactions, a far more compelling argument would be that the field itself A is dynamical, it's a it also changes, but then you have to give it dynamics. And then I argued that this combination here is also gauge invariant and includes derivatives of the gauge field. So that's the story of abelian gauge theory. So far we did that. Now it so turns out that nature didn't choose to be modeled by just abelian gauge theory. Nature chose to be modeled by non-abelian gauge theory. So I guess I better tell you what that is. And that's the objective for today. The good news is that there's no additional ideas really that you need to know about in order to understand non-abelian gauge theory. We're going to carry out exactly the same steps as we did to build an abelian gauge theory, and you'll see that we only have to make technical modifications in order to get things to work. I mean, there are technical difficulties we'll have to solve, but conceptually, there are no real new ideas. And again, to stress, this is all classical. We're talking about classical gauge theories here. The quantum story is for next lecture. And the quantum story will be to find a unitary representation of the Poincare plus local gauge group. So far, these are just representations. Nowhere is it stressed that they're unitary. They're just Now, I'm not going to tell you the full non-abelian gauge theory story. I'm going to focus on very one particular gauge group, namely SU2. This one's certainly relevant for the standard model, SU2, but to do things in mega generality, we need to have arbitrary connected Lie groups. Well, it turns out that there's nothing really, there are only technical difficulties that are encountered in dealing with the more general case. And once you understand the SU2 story, you understand almost all the story for the general Lie group case. So, it's like knowing the representation theory for SU2 basically tells you how to do representation theory for general Lie groups. The same sort of story happens here. Okay, well, now we got to build such a theory, we have to decide what is the local gauge group for this thing. And the answer is the local gauge group for an SU2 gauge theory, by analogy with the abelian case, is the group of all transformations which apply an SU2 transformation V of x, a different one at each location in spacetime. So that's what the local gauge group is. So, and we want our theory to be invariant under this. So we need to choose some kind of representation. And just as before, we're going to imagine that we have fermions, and they will furnish our representation. That's how we'll start the story. But now this is a 2 by 2 matrix, right? V of x is an element of SU2. So what does V of x look like? Well, it's a 2 by 2 matrix. V naught naught x, V naught 1 x, V1 naught x and V11 x subject to the constraint that the matrix is unitary and has determinant 1. And that turns out to be equivalent to the constraint that Vjk squared, the jkth entry of this matrix, the sum of all these entries squared equals 1. If my memory doesn't fail me. Yeah, that's one constraint. And the other is that, no, I think that's it. I think in the end that implies everything. Yep. The identity doesn't lie in, oh yeah, right, thanks. Right, yeah, that's a good point. That constraint couldn't have been correct because the identity doesn't lie. Well, I can't remember off the top of my head if that gives us unitarity or not. I believe that this does imply this, but I cannot be sure. So we have a theory invariant under a choice of, turns out, 3 variables, 3 real variables, at every location in space-time. And we have to choose how this thing is going to act on the field content of our theory. How does it work? It could act in any number of imaginable ways. However, we're going to take it to act linearly. We're going to introduce 2 spinor fields, psi 0 and psi 1, let's say. 2 independent spinor fields. So this subscript here is not to be confused with the spinor subscript. And we let this 2 by 2 matrix act on these 2 spinors according to the following recipe. So we that's how it acts. Gives you just a linear combination of these 2 spinor fields. That's one way of doing it. We could have chosen boson fields and done the same thing, or we could have dreamt up more crazy ways that it could have acted. Indeed, all of these can play a role in high energy physics. We could have chosen, instead of the spin half representation, the fundamental representation here, we could have chosen a spin 1 representation and had 3 spinor fields. There is no limit to the number of ways that this group can act. This is just one way, one particular arbitrary choice for how we're going to take this local gauge group to act on fields. And now we want that our theory is invariant under this. Now, there's the easy invariant terms and the hard ones. So let's do the easy ones first. And to help with that, it's useful, I think, to think of these two spinor fields as kind of like one bigger field with two spinors stacked on top of each other. So we build a doublet field. So this is an 8x1 So this capital psi, this doublet is like an 8x1 vector. It's obviously a vector. It's got 8 entries. And it transforms under the Poincare group just like two independent spinors. Actually, there's one trivial way to get this group to act on a spinor field, just one spinor field. We could have used the one-dimensional or spin zero representation of SU2. Under that representation, you could get one spinor field to transform as psi equals psi. So that, you know, the trivial representation is a representation, but it's a pretty boring one. This is the first non-trivial representation here, the spin half one. So we build that guy. And then how does the gauge field act? Well, how does the local gauge group act? Well, it takes our doublet of spinors. All right, these are already 4x1 vectors. And it applies this matrix here. It's the 4x4 identity. Here's another 4x4 identity. That's how the local gauge group acts on our doublet in this highly reducible way here. All right, now, what are our invariant terms? Well, there's some easy ones, just like there was for the abelian case. You could take psi bar psi, where psi bar, in this case, is defined to be psi bar psi is defined to be just the normal psi bar summed over the diagonals like that. You can check that that's invariant. And you could do the other one. Take some gammas in there, gamma matrices, where But then we more or less exhaust all the possibilities to write down invariant terms. At least all the invariant terms we can write down do not involve derivatives. We can't write down invariant terms, Lorentz scalars, which involve derivatives for exactly the same reasons as for the abelian gauge theory case. So it's, nothing's really, the argument's exactly the same, why it doesn't work. And then we're going to take recourse to exactly the same argumentation that we used in the abelian case. Now we're going to introduce a covariant derivative with the help of a parallel transport field. So what we're doing by introducing a parallel transporter is we're going to another representation of the local gauge group, one that includes this additional data of a parallel transport object. But this time, u, y, comma, x isn't just a number. U, y, comma, x is also an element of SU2, a 2 by 2 matrix in this particular case. And it transforms under local gauge as, do I have daggers or not daggers? Daggers. Like this. So suppose we could find this 2-parameter family of 2 by 2 matrices for all pairs of points in space-time. And suppose it really fulfilled this constraint here. Then we'd have an object that we could use to build a covariant derivative just exactly the same way as we did for the abelian case. The only subtlety is this is now a matrix rather than a number. There it is. So n is just a unit 4 vector. So this is the directional derivative, but the covariant derivative is when you remove the n and use the basis vectors like what I did in the previous lecture. So here is an object, a very useful object because it transforms in a nice way under local gauge transformations. And I'll write that way down in a second. So this is exactly by analogy with what we did with the abelian case. There's really no difference so far, except that you've got to mentally keep track of this u as not being a number now, but being itself a 2 by 2 matrix depending on 2 space-time locations. Now remember that we also, this is a solution, but it's a pretty non-local solution. You need to have some extra field which apparently depends on 2 independent space-time locations in a possibly very complicated way. But we reduced the data we needed to specify to make such a theory invariant by realizing that, of course, we don't really need to know what the parallel transporter is at every every pair of locations in space-time. We only need to really know it for infinitesimally nearby points. And that's local information, and we're going to capture what that local information is now. So we're going to build local theories. We only need to know this parallel transporter for y is very close to x. All right, let's assume that this is differentiable. This u is differentiable, and we'll capture exactly what data we do need to know in order to specify this guy to first and second order. Well, because u is an element of SU2, and namely the fundamental representation of SU2, u has the expression of e to the I times a x, where A is a 2 by 2 matrix, a Hermitian matrix of trace 0. It's often convenient to work with the exponential representation for unitary matrix groups, especially when you're talking about nearby group elements, nearby things, because then these guys here must be an element of the Lie algebra. There's something close to the identity. Any unitary operator which is close to the identity, these exponents here must be elements of the Lie algebra. Now, it's sort of convenient. I mean, you can do everything I'm going to do without choosing a basis, but I'm going to choose an operator basis to express this A. But you can certainly do the whole story without making a basis choice. And I mean, that's certainly the trendy and cool way to do it amongst the physics community, is to do everything basis independent, right? Because then it's manifestly invariant. You know that everything you write down is invariant. But the minute you come to actually do a computation on a computer, you're going to have to put the numbers into the computer somehow. So you have to choose a basis. So the emphasis certainly in this course is on being able to do computations. And so I could put everything in sexy coordinate-free notation the whole way through. But then when you come to actually do a computation, you have to laboriously put in the basis. I'll put in the basis now, because we're going to anticipate that pretty soon, indeed next lecture, we're going to start talking about how would you do an actual computation with a quantum version of this theory. So let's make our basis choice. We're going to express this 2 by 2 matrix as a linear combination of some matrices, right, that span the set of all matrices which are Hermitian and traceless. Well, we have our favorite ones. They're not the right ones, but they are matrices which are pretty useful in some ways. And I put a 2 here. All right. So any 2 by 2 Hermitian traceless matrix is a linear combination of 3 basis matrices, and the ones we take in this course will be the Pauli sigma matrices. Guess you're used to seeing these things by now. And warning, in the literature and textbooks, there are a trillion different conventions. We're going to take the quantum information convention, I think, which is to say no, we're not. We're going to take another convention. With a factor of a half. There's a reason for that factor of a half. And the factor of the half is so that they form a Lie algebra. The bracket operation is nice. I think that's right. Oh, well, let's just do a check. Vectors of 2 are super annoying, so you've got to get them right. All right. Yeah, it works. So this factors of 2, if you don't keep track of them, then, well, it doesn't make any difference really for the classical gauge theory case, but these factors of 2 can be annoying when you do the discrete version later on. So we choose this particular set of 3 2 by 2 matrices to express this Hermitian traceless matrix as a linear combination. Done. So that means, what do we need to specify this comparator object Okay, I've used the same symbol. I apologize for that. So because for arbitrary u in SU2 you can express u like this. Don't think of this as the parallel transporter yet. This is just... All right. I'll fix this simply by saying that we'll get rid of the x dependence here. Good. If you have a 2 by 2 determinant 1 unitary matrix, you can always express it as the exponential of a traceless Hermitian matrix, which in turn you can write as a linear combination of 3 Pauli operators if you want. That means to specify You need 3 real numbers. That's important. Yep.
Why do we need this factor of a half in
The question is, why do we need this factor of a half in the basis representation? You don't. You could have easily well have taken that factor of a half out, but I believe I chose it because later on it makes an expression match a standard expression in a textbook. This factor of a half certainly doesn't matter. This one here, because I could just redefine alpha. Alpha are 3 independent numbers. So it's up to you if you put the 2 there or not. I'm choosing to put the 2 there. Later on, it'll make something look nicer. However, the factor of a half in the Pauli's is really to make the bracket, the commutation relations look nice. If I hadn't have put the half there, then I'd have halves or 2s on this side here, which isn't as nice, right? We've got to the stage where we're trying to mimic this derivation of the covariant derivative by introducing this parallel transporter U. And we realize that we only need that particular data to do the covariant derivative. So writing that as something that depends on x, well, and n, obviously, we can expand, right? We assume that this thing is differentiable in the first argument. So let's just expand, and that's just as simple as taking a Taylor series up here. It's a 2 by 2 matrix, which depends on a small number. You can do Taylor series for matrices just as well as you can do them for normal functions. A matrix is just 4 normal functions in this case. And that Taylor series you can write like this if you really want. Now there's an implied summation over repeated indices here. All right, that's just what it is, right? And this G is just some constant that we pull out because it'll also have a particular meaning later on in the story. Yeah, maybe I'll just call this A or B. And to first order, in epsilon, this B is 0. and to second order it behaves like this. Just so that that makes a bit more sense. Okay, let's go back to the covariant derivative definition and write it in terms of just this infinitesimal data now that we have.
Excuse me?
Yo.
I have a question. When there's the first line B, how can the second line appear A?
So the question is, if there's a first line, if there's a B in the first line, how can A appear here? So B, this is a 2 by 2 matrix, which depends on epsilon, n, and x. And we want to expand this in smallness of epsilon. So the first observation is that it's the exponential of some Hermitian traceless matrix, which depends on epsilon, n, and x like that. By assuming that it's differentiable, this matrix B has to be 0 to order epsilon plus some epsilon times by something else. So this B is epsilon g n mu a mu j sigma j over 2. I didn't want to write an A here because I have the A here, and so it looks like I'm talking about the same thing. But here I actually pull out the epsilon dependence. That's the definition of the covariant derivative, right, using this parallel transporter. But now we've got it in terms of local data instead of needing to know the parallel transporter between any 2 points in space-time. So we can use this local specification, get rid of the epsilon, and then we're done, right? We have something that will look like a covariant derivative. And indeed, there is nothing new. It works exactly the same way as last time, and we get this expression for this covariant derivative here. The only difference being now, of course, that this is a matrix. And in particular, it's an 8 by 8 matrix. Because this 8 by 8 matrix is acting on 2 4 by 1 spinners in a way that I wrote out several boards ago. Now these coefficient fields here, AJX, well, they're not just arbitrary numbers. We don't have 3 arbitrary numbers at each location in space-time. They themselves have to obey some transformation rules. They have to give a representation of the local gauge group, and that's determined by this equation here. We know that ux plus epsilon nx under a local gauge goes to v x plus epsilon n x v dagger x. So it better be the case that when I do a local gauge transformation, that A is going to transform, and it's going to transform in a particular way, and that way is determined by this equation here. So we're going to substitute this into here and expand everything to order epsilon. And I believe I left this as an exercise. Well, I'll write out the answer and then I'll give some helpful hints. So this 2 by 2 matrix, well, it's an 8 by 8 matrix which is acting reducibly on two spinors. This big matrix here transforms under local gauge to Vx. V dagger x. And that's an exercise. But I'll give you a little hint for how you can do this exercise. You've got this expression at order 1 when you substitute this thing into here. That's really kind of the complicated expression. It's this one. The other term is kind of just trivial, right? This VA blah 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 V dagger, that first term here, just comes from this order epsilon term here being substituted into here. And if that's order epsilon, then that has to be order 1, and then we're done, right? The V's just come down. So then the actual difficult bit is to deal with that thing there. And there's a trick to dealing with that thing. And that is that this, and I'll just write out one term and I'll still leave the rest for you. It's just the directional derivative of V of x, V dagger of x, plus order epsilon squared. That's a super useful thing to note. And actually, you know, when you see that, you can sort of pattern match that second term here into existence. And then I hope it's not really that big of a chore to work out that that's how this 8 by 8 matrix has to transform under local gauge transformations. Well, that doesn't quite get us to a nice transformation law. We still have V d mu V dagger x. It's not quite trivial to proceed here. Well, we can do it. So this is the core subtlety that the non-abelian case has over the abelian case. So in the abelian case, we just had d mu alphas, alpha being the phase, and now we've got this kind of 4 by 4 thing, 2 by 2 thing, or in our representation, 8 by 8 matrix. And actually, I'm going to sort of cheat and not do the full computation. I mean, we can do it, but it's just it's a bit more tedious. So we're just going to deal with a case where V is infinitesimally close to the identity. You can do the full general case, but it just gets a bit more ugly. So according to the argumentation I gave about 2 by 2 matrices inside the group SU2, we know that it's the exponential of some alpha j sigma j's over 2. Right? Some numbers that depend on x. And so we have to, we have to compute this thing. So we can do that infinitesimally just using Taylor's theorem. The difficulty is, of course, if these numbers are not small, then we have some non-commutativity going on. I won't, I have actually worked out the details of this, but it's not really, it's not worth it given how we're going to use this information. So just assume that alpha is small, and then we can expand the left and the right terms here to order alpha. Now this derivative here just knocks off that constant term, and so we're left with just something at order alpha, namely minus I d mu alpha sigma j2. This thing here is alpha squared, so we only have one term to order alpha. So under a gauge transformation, like of the form up there, we can write things to order alpha and get another expression which is perhaps more helpful for building invariant terms. Under a local gauge, A now transforms as A mu j sigma j over 2, the nothing bit, plus 1 over g d mu alpha j, plus, and you get one more term. This term didn't appear in the abelian case because the sigmas don't commute, right? This sigma j here doesn't commute with the sigma k up in the alpha, in this gauge field. We've got a commutator that appears. So this is new to the non-abelian gauge case. The abelian case, we didn't get that. So now we can understand we can see what infinitesimal local gauge transformation does to a covariant derivative term like this. The full case of a non-trivial gauge transformation, which is not infinitesimal, you know, where V is big everywhere, is not covered by what I'm about to say, but does follow if you work it out. So we start to compute how does this transformation, how does this thing transform under gauge transformations? Well, how does psi of x transform under local gauge transformations? Well, under an infinitesimal one, it goes like this. And then the question is, like, if we combine that with that rule up there for this gauge field, does it cancel out? Do we get a nice transformation law for the covariant derivative term? So certainly, by analogy with the abelian case, we have a guess for how we want this thing to transform. We want that after a local gauge transformation, this doublet of spinors transforms to just a v of x times d mu of psi of x. We want that it transforms in exactly the same way as this. So all that stuff happening up there with the a had better cancel what happens when the derivative term hits this term here and when the second term in the covariant derivative, which is not here at the moment, has to commute with this sigmas there. Well, of course it does all work out well, but we still have to check it. So if you like, this is an exercise. Although it's not really a difficult exercise because I'm going to write out all the steps. So under an infinitesimal gauge transformation, not a big one, but a little one, this covariant derivative of the doublet transforms like this horrible mess to order alpha. All right, so let's just look at it and see if everything cancels out nicely.
Sorry?
Yo?
Upper right corner of the artboard, we had the commutator with a k on the alpha and a j on the a, matching the a on aj on the left side of this mapping. And on the lower board, we now have j's on the left side and the commutator.
Okay. So the question is, why do we have k's in that commutator up there and j's and k's here? Well, they're dummy variables is the answer. Since we're summing over them, I could have called them j and j prime or k and k prime. They don't match. There's a summation over those repeated indices. Yeah. All right, so we look at, you start multiplying this stuff out to order alpha, right? Not alpha squared, just order alpha. And let's see what kind of terms happen. Well, we get the nice term, right? D mu psi. We knew that was going to come. And we get stuff to order alpha as well. And it turns out if you just multiply out all the terms, I mean, you're only going to have to deal with 4 plus 1, 2 terms, 6 terms, I believe. It's just not so hard. You should get that. And that's the infinitesimal version of Vx d mu psi of x. So we get that at least under infinitesimal gauge transformations that this covariant derivative term is transforming in exactly the right way. Now comes the physicist bit. You know, so far everything I've been saying can be totally rigorous. Even the arguments I've been making are essentially rigorous. It's just I'm not taking the time in this course to spell out all those steps. But the physicist bit of the argument is that to get it for a big gauge transformation, you just exponentiate, meaning you just repeat this transformation many times, and using the identity that 1 plus, you know, any matrix x over n to the power n is e to the x. That's what physicists mean by exponentiating. So you take this transformation, which you know to be correct to order alpha, and repeat it many times, and it adds up, right? You get this kind of expression here. And then e to that is, well, it is just v of x, right? So we're done, right? Well, there's sort of issues with connectivity of the group, of the local gauge group that you have to worry about. Yeah. I'll just write some issues, but this is good enough for physicists. And that's what we're doing in this course. There is a way to make this all perfectly rigorous, but we'll have to get into gauge fixing a bit more to talk about that. Well. Now, we're almost there. We're almost down at the stage where we can write a Lagrangian density, a classical Lagrangian density, which is invariant under this local gauge group, which has dynamics, which is not completely trivial. Now we need to get to build a Lagrangian density term which gives dynamics to these fields A, J, mu. Now, in the notes, I've just used this trick that we already noticed at the end of the previous lecture. Namely, look at the gauge, look at this, the behavior of the commutator of these covariant derivatives under local gauge. Well, thanks to this derivation here, if we believe the exponentiation business, we know how that's going to transform. That transforms like this. So we have an invariant term involving derivatives and a's. Right? We have this commutator. This is the curvature. And for those of you who are familiar with this language, it's the curvature of this fiber bundle. And you can evaluate it. That's a very short exercise. And you get this expression, f mu nu, I put them downstairs, mu nu j sigma j over 2. So that's really just a matter of putting in the definition of the covariant derivative and noticing that mixed partials commute, mixed partial derivatives commute. So the only difference between this thing in the non-abelian case and the abelian case is that we've now got that there's this, that it's a 2 by 2 matrix instead of a number. And I have to tell you what f is. Yeah, I'll do it this way. It has some familiar looking terms and some slightly unfamiliar looking terms. There we go, it's that 2 by 2 matrix there if you work it out. So there's something, this looks familiar, right? It's just d mu a mu, d nu a mu. That looks kind of like the original curvature tensor what we had for the abelian case, but here, that is one interesting term right there. Curvature tensor now depends quadratically on these degrees of freedom A. So in the abelian case, I didn't stress that very much in the last lecture, but you probably would have noticed that the curvature tensor only depend linearly on A in the abelian case. But here it depends quadratically on A. And since we want to build ourselves an invariant term in the Lagrange density, we have to take that curvature tensor squared, which means that this term here is going to appear squared and also multiplied by these terms here. We're going to get cubic and we're going to get quartic terms. So gauge invariance here, requiring that the Lagrange density is invariant under local gauge transformations in the non-abelian case, turns our theory from a quadratic theory, which is essentially not interacting, into a interacting theory. So just the A theory alone, the theory of these gauge bosons, becomes extraordinarily non-trivial, even in the classical case. So I'll make a couple of comments about that in a second. But first, let's build ourselves a nice Lagrangian. So under local gauge, we find that this curvature tensor transforms in a very nice way indeed. Transforms like this. So transforms by similarity transformation, which is fantastic because that means we can build. That's also an exercise, not a very difficult one. So that we can build an invariant term, a Lorentz scalar, that's invariant under this by taking a trace. Simple as that. Okay, this is invariant under local gauge transformations because, well, I should use k's here, right? Just the dummy indices, but hey, it's always easy to get confused. Because this guy transforms like that, v times v it v dagger, and this also transforms like v something v dagger. The v and the v daggers cancel in the middle, the v and the v daggers cancel there. So it's invariant under local gauge. And thus we can build a Lagrangian that's invariant under all local gauge and Poincare transformation. All right. So this term here is invariant, but if you work out the trace of a Pauli times by another Pauli matrix, then you get you get a half only when j equals k. So you get a delta j, k in these repeated summations here. So I feel like I've got an extra factor of 2 now. I believe that's 1/8. Check the 1/8. Just to make sure our factors of 2 have been preserved all the way through. And you can build then a Lagrangian that's invariant under local gauge and Poincare symmetries by, well, any scalar multiple of this term. I've chosen by tradition to use -1/4 f mu nu j squared. So this Lagrangian there is invariant under all these symmetries. However, this is a much more non-trivial affair than the original abelian case that we studied. So in the abelian case, the electrodynamics case, this curvature term here is quadratic in that gauge field A, which means that the gauge field dynamics alone not very interesting. I mean, there are some subtlety to do with gauge invariance, but it's just the wave equation. It's just Maxwell's equations, what comes out. Right? So the sub-theory where you just look at the gauge field alone as the dynamical content and there are no fermions, that's, in the abelian case, a relatively straightforward entity to solve. You have to deal with gauge symmetry, but that's just equivalent to doing electrodynamics with a gauge in terms of a gauge field A. So we're kind of used to that. There's many well-developed tools to solve electrodynamics in terms of gauge fields. But in the non-abelian case, the gauge field alone, if you turned off the matter, so if you said there's no fermions, let's just look at the Lagrangian just for the gauge field alone, in the classical setting is extraordinarily non-trivial. Well, it's quartic. This term there is quartic in the A mu's. All right, we can see that up here. When you square this tensor here, you're going to get some nice quadratic terms. They look familiar and nice. Plus you get some cubic terms where these are the cross terms coming from that times that. And you get some quartic terms where you got this commutator squared. So in the classical case, we have Maxwell's equations here for U1. We know the solutions in free space are waves. Done. Here we have a totally different proposition. We have a nonlinear equation of motion for the classical gauge field for these A mu J's. And solving those equations is a much more non-trivial task. Now there are various approximations you can make at this stage, and one of them is to say that G is small. Right? You know, this is our standard perturbative way of dealing with difficulty in physics. Let's just pretend that G is small, and then we know what the solutions for the classical gauge field will be when G is 0. So when G is 0, the solutions will just be waves again. We got this matrix degree of freedom, but that just means we have some number of copies of our original gauge field. So that certainly works, and you get a lot of intuition that way into the classical solution. However, there exist in this nonlinear regime, where G is not 0, all kinds of new solutions that couldn't exist for the U1 case. We get these so-called instantons and soliton solutions to these nonlinear equations of motion in the classical world. So this is a hint, right? It's a hint that this is going to get hard. Because when you have a classical dynamical system that's nonlinear, that's already hard. Right? You don't even have to do quantum mechanics to know that that's hard. But if you want to quantize that, then there's lots of ambiguities that come up when you try and find a quantum system that in its classical limit is modeled by this nonlinear classical system. And we're going to have to confront all these difficulties when we quantize these gauge fields. We can solve them both in the perturbative setting and in the non-perturbative setting. I'm actually going to go into some details about that in the coming lectures. But for now, we are done with our description of classical gauge theory. It's this theory that we want to find a quantum analog for, both in the abelian and non-abelian case. And we're going to do that by two seemingly very different ways, very different approaches that, as far as I'm aware, haven't been proved to be equivalent yet. Namely one perturbative using path integrals, and namely one non-perturbative using lattice discretizations. But that's for next lecture. But for now, thank you very much.